Hi, welcome to Plutus IAS. In previous class, we covered collision theory, and today we are going a step further and will be discussing what is known as activated complex theory, which is also known as transition state theory, and most oftenly known as by a name which is called as absolute reaction rate. So, in previous class, as we talked about that, the collision theory can only be applied when we are talking about a gaseous phase reaction, that too between two molecules. That means a bimolecular gas phase reaction. But in reality, whatever many of the reactions that we do in the real world, they either occur in the solid state or majority of them occurs in the solution. So that means only 5 to 10% of the reactions the collision theory is actually applicable. But the collision theory has not just limitation regarding to the type of reaction. It is also limited to the probability factor. That many often times the probability factor that is obtained from collision theory have a much higher value which can never be attained in the real life. Because of all those limitations, we needed new theory which is given as the transition state theory. Now this theory can be applied on any type of reaction, whether it is occurring in the solid phase, liquid phase, gaseous phase, whatever the type of the phase of the reaction, it is applicable to all of it. And this theory links both the chemical kinetics along with thermodynamics. And because of these properties, this reaction is also called as absolute reaction rate theory because of its nature to be applicable on various types of reaction. Now, what does this reaction do? It combines, it uses, it uses knowledge of quantum mechanics, knowledge of quantum mechanics, of quantum mechanics and thermodynamics, thermodynamics to explain factors affecting kinetics of a reaction. Kinetics of a reaction. Now, it states it states that the reaction proceeds between two species. The reaction proceeds via formation of a reversible activated complex which has the highest energy of the system, which decomposes for the formation of product P. So let's say this equation had some equilibrium constant K, because this is a reversible reaction. Now, the transition state theory suggests that the activated complex that is being formed in the reaction, it will form very fast and decomposes for the formation of product. So the rate of reaction is based on two factors. Rate of reaction, it is based on the concentration of the activated complex that we are taking multiplied with the frequency of decomposition of activated complex. What is the rate of decomposition of the activated complex per second? Now, since it is a fast equilibrium, we can use equilibrium approach using equilibrium approximation method of the chemical kinetics. We can find that the equilibrium constant for the formation of activated complex will be given by concentration of the activated complex divided by the concentration of reactant A and reactant B. So the concentration would be given by AB hash equals to K equilibrium A multiply B. So we have found the concentration of the equilibrium constant which is required for the reaction. For the second part, now we need to find the frequency. Now, how can we do it? So, for this, we require quantum mechanics that states that the energy of system of any system with progress will be that this is the energy of both the reactants, and The activated complex represents the highest mechanical state, quantum mechanical state of the system. And as per Bohr correspondence principle, using Bohr correspondence principle, that whenever a system is in its highest quantum mechanical state, at that point the classical mechanics and the quantum mechanics will give exact same answer. So that means from the energy given by quantum mechanics is h nu, whereas it will be equals to RT, not RT, yes, for a state it will be given by RT. So here the frequency will be what? Nu will be RT upon H. But since we are talking about molecules, the number of molecules play a significant part. So we'll represent this R in the form of Kb, which is Boltzmann constant divided by N naught. Wait, sorry. It should be given by Kb. Kbt, Kbt divided by H, and this Kb can be written in terms of R upon N naught H. Here, I'm using N naught to represent the Avogadro number because for the reaction I've already taken A and B. So to represent Avogadro number, I'm using the N naught. So now we have the frequency, we have the concentration. So the rate can be written as, the rate will be equals to, the concentration was, the frequency was RT N naught upon H multiplied with equilibrium constant for activation, concentration of A and concentration of B. Now let's compare this equation for normal rate of reaction with rate constant K2, A and B. So here by comparing, I can find that the rate constant K2 for the product formation is RT and not H K equilibrium star. And we know that the value of K equilibrium star is given as Ln K equilibrium is minus delta Gibbs energy for the activated complex by RT. So this is the value that we know. But the above equation in the form of K equilibrium, so we'll write it as, and let's take it to the side. Taking ln, it can be written as ln of K2, ln of RT, N naught by H plus ln K equilibrium star. Now we know this equals to this, so we can directly utilize it as ln of K2 ln RT N naught H plus, sorry, not plus, it will be minus delta G naught of RT. We know that the delta G naught can also be represented in terms of enthalpy of activation minus T delta S in terms of delta G naught. Since we are talking about activation, this enthalpy can be represented in terms of change of internal energy of the activated complex minus of delta NGRT minus T delta S naught. So putting all this value, it will become log ln K2 equals to ln RT N naught H plus minus delta E naught upon RT minus delta E naught RT minus delta Ng RT upon RT plus it will be minus delta S naught T delta S RT. This is entropy of activation. So let's see, delta E naught minus minus, okay, everything is there. Now putting in the values, it will be ln of K2 ln of RT by N naught H minus, this is energy, internal energy of the reaction RT E naught minus, it will be plus delta Ng, RT will cancel out, it will become just delta N, it will be minus, wait, this will be plus delta Ng RT and this will be here plus and this will be right here, it will become minus. So delta NGRT, T delta S, it will be delta S naught entropy of activation divided by R. Now let's try to what we have E naught. So taking ln minus delta G LT R naught exponential. Now removing ln, I can write it as the value of K2 will become RT N naught H, it will become exponential of minus of delta E naught star RT exponential of minus of delta Ng exponential of minus minus, this will become plus. मैंने माइनस ओपन ही नहीं किया था यहाँ, ये प्लस हो जाएगा, this should be deleted now, better. Exponential of delta S naught star upon R. This is the value. Now the problem is, in this equation we don't have the value of E naught, and please do not by mistake mark it as activation energy. So first we need to find the value of delta E naught. So for this we will take the relation d ln Q2 by dt, which was given by Arrhenius, that states that it will be equals to EA upon RT square. So that means the above relation will be converted into this form. So if I take differential of ln K2 with respect to T, it will give me the ln RT N naught upon H. Wait. It will give us 1 by T minus delta E naught RT square, it will become plus delta Ng0 delta S naught R. This will give us 1 by T. So solving it, taking T common, it will become EA upon RT equals to 1 plus del E naught activation upon RT, and when we solve it, the value of EA will come out to be, the value of EA will be equals to RT plus delta E naught star. E naught. So this will become as EA is equals to minus of RT. So now we have the value. Using this, the equation of ln K2 will become ln RT by N naught H plus minus of exponential minus of EA. Why instead of that, let's directly put it. I'll go for it. The value of K2 will become RT N naught H multiplied with exponential of minus of EA, it will be plus of RT RT cancels out, exponential of minus of delta Ng multiplied with exponential of delta S naught star R. Here this will become 1. Let's separate it. It will be K2 RT N naught H exponential of minus EART. Now let's take it to entirely to the other side. Now this will become plus 1. I can write it as exponential of 1 minus delta Ng and multiplied with exponential of S naught activation of entropy of activation divided by R. Now if I compare it, everything except for the T part, this is what your pre-exponential factor A, sorry, this entire value will be equal to your pre-exponential A, which is directly dependent on temperature. This will now is equivalent to your Arrhenius equation minus EA upon RT. If I compare it with collision theory, this particular factor right here represents your steric factor P, which is your steric factor. So now, this is how we derive the activated complex theory. Now, in this equation, you can see that now we have the parameters delta Ng, we have the entropy function, we have the number of molecules, RT, activation energy, everything. So now, based on entropy of a species, I can predict the steric number. Now, if the species is taking place in gaseous phase or other phases, this factor can also be decided. So, all of this reaction on the equation, we can say that this equation can be used for everything. This equation can also tell you the effect of pressure on the equation using the value of delta Ng, as we have used in case of equilibrium. So it predicts the effects of pressure. What will be the effect of pressure if a gas is occurring in the gaseous phase, whether we increase the pressure, decrease the pressure, or keep the pressure up to a zero value. Okay, so I hope this would have cleared all your doubts. Now for the next part, we'll try to cover the limitation and some extra important factors that ACT explained for explaining the ionic strength of a solution, the effects of pressure, and how we utilize them on a daily basis in the while determining the chemical kinetics when we are conducting reactions in the liquid phase and the when for the conductivity and other parts. Okay, so I hope this would have cleared everything now, and we'll see you in the next class. Bye then.